In this lesson, we're going to talk about angular displacement, angular velocity, and linear velocity. And I want to start off by just talking about this word displacement. And of course, you got to spell that right before you can talk about it. So let's see what I can do here. It's displacement. And displacement has to do with your change in position. In other words, how far have you traveled? Right? When you're talking about displacement, you want to know how far you've traveled. So when we typically talk about displacement or how distance traveled, we think in terms of linear displacement. Oh, today I walked 5 miles or I drove 50 miles. Those are all displacement measurements, but they're given in linear terms, miles or feet or meters. We are also going to focus on what we call angular displacement, and that displacement is measured in radians. So for example, we know, and let me draw this a little bit bigger, we know on the unit circle, if you were to start at the coordinates 1, 0, and you were to travel around the edge of that unit circle, you would have traveled 2 pi radians. If you only travel a quarter of a turn, that's pi over 2 radians. If you make it halfway around the circle, that's pi radians. Those are all examples of angular displacement. And it's based on how far you've traveled around the circle. Now, typically when we're traveling in a circular motion, we talk about revolutions. So for instance, a tire might be spinning at, it might make a turn. A full turn is 1 revolution. And although we're going to spin in the counterclockwise direction like we do on our unit circle. So this is called 1 revolution, when you make it all the way around. We know that that's 2 pi radians in terms of the angular measurement, but the act of spinning around 360 degrees is called 1 revolution. If you want to convert revolutions to radians, you multiply by 2 pi. And so let's just keep that in mind as we take a look at this first example. If you want to go from revolutions to radians, you multiply by 2 pi to figure out how many radians you've gone. Okay, let me give you an example because I sort of mumbled through this. So the first calculation you're going to have to make in this lesson is you're going to have to determine the angular velocity, or excuse me, the angular displacement. Velocity is coming later. And we're going to do that in radians if we're given a certain number of revolutions. So at the end of the last slide, I said if you want to convert revolutions to radians, you simply multiply by 2 pi. So for this calculation, I'm going to take this 4.5 radians, I'm going to multiply by 2 pi, and I'll be able to tell you the angular displacement. So that's going to be 4.5 times 2 pi. And notice it says round it to the nearest tenth. That means that we can use our calculator and we can have a decimal version for the answer. It doesn't have to be in terms of pi. So when I multiply this out, 4.5 times 2 pi, if I'm doing it in terms of pi, that's 9 pi. But when I multiply this out on my calculator, I end up with 28.3 radians. And that's the answer that we're looking for. And just to remind you what that calculation means, if you're going to spin around 4.5 times, so 1, 2, 3, 4.5, you end up over here. If you were to unroll that and string it out, you would have to line up the radius of this circle 28.3 times. So there'd be a radius and 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 a radius 28 times and then a little bit extra to be the same length as a turn of 4.5 revolutions. That's what we're calculating in terms of displacement. We're trying to find out how far, in terms of angular displacement, we've traveled with 4.5 revolutions. Okay. So we've talked about displacement. Now we're going to talk about velocity. I mentioned earlier that displacement had to do with how far you traveled. Well, velocity has to do with how fast you got there. And typically the way we measure velocity is the distance traveled over the time, right? So miles per hour or meters per second. For angular velocity, we're going to look at radians per second or radians per unit time, okay? That's what angular velocity means. And we're going to label that angular velocity with the Greek letter omega. It's like a fancy W. And this formula here tells us that the way we get the angular velocity, omega, is to take our radian measure for our angle and divide by the t units of time. So it's the theta divided by t, or angle divided by time. That's how we do angular velocity. Let me show you a quick example. Here in example 2, we're asked to determine the angular velocity if 7.3 revolutions are completed in 5 seconds. So we want to do the angle in radians divided by the unit of time. Well, right now, our displacement is not measured in radians, it's measured in revolutions. So we have to convert that to radians first. That would be revolutions times 2 pi. So to do the displacement, we do 7.3 times 2 pi, which is like 14.6 pi, which is 45.86725. And that's radians. And then to figure out the angular velocity omega, we're going to do 45.86725 divided by the 5 seconds. And when we do that, we end up with approximately 9.17 radians per second. Now, because I've read the directions and I remember that it says round to the nearest tenth, I'm going to put this answer at 9.2 radians per second. So my angular velocity for this problem is 9.2 radians per second. Convert the revolutions to radians, then divide the radians by the time. Radians divided by time. That's how you get your angular velocity. To avoid mistakes when computing with units of measure, you can use a procedure called dimensional analysis. In dimensional analyses, unit labels are treated as mathematical factors and can be divided out. Back in chemistry class, I think they used to call this an action line. In example 3, we're going to refer to the application below, which came from the beginning of the reading, and we're going to determine the angular velocity in radians per second. So keep in mind that our answer needs to be in radians per second, and we're computing angular velocity. So first of all, let me remind you that angular velocity, which is omega, equals theta over time, right? Radians per second is what we're shooting for. So here's the story. The Children's Museum in Indianapolis, Indiana houses an antique carousel. The carousel contains 3 concentric circles of animals. The inner circle of animals is approximately 11 feet from the center, and the outer circle of animals is approximately 20 feet from the center. The carousel makes 2.58 rotations per minute. And then the rest of this is just asking us to do what the question already asked, which is to find the angular velocity in radians per second. One thing I want to note is 2 5/8 is the same as 2.625. So I'm just going to use that decimal instead of 2 5/8 just because it's easier to type in on my calculator. So here's how this works. We are trying to get to radians per second, but our information is given in rotations per minute. So we have to get from rotations means revolutions, so we have to get from revolutions per minute to radians per second. And this dimensional analysis works like this. You write down, including the units of measure, exactly what you're given. And keep in mind that this word per is the same as like a division or a fraction. So for example, I know that I do 2.625 revolutions, and I'm going to write REV for revolutions, in 1 minute. And I know that there is 1 minute every 60 seconds. And I know that there are 2 pi radians, equal to 1 revolution. And so these are all multiplied together, so we can do cross-canceling just like we would with fractions. So check this out. My 1 minute here, I was going to actually not use a highlighter. I was going to use the ink pen. My 1 minute here will cancel with my 1 minute here because there's one on top and one on bottom. My 1 revolution here will cancel with my revolution there. And I end up with only 2 units left. I end up with seconds in the denominator and radians in the numerator. And that's what we want. We want radians per second. So now I can multiply this out and reduce it and get my answer. So in the numerator, let me switch to a different color here. In the numerator, 2.625 times 2 pi, when I multiply that out, I get 16.4933 radians, because radians are still on top. And in the denominator, I get 1 times 60, which is 60 seconds. And then if we go ahead and do 16.4933 divided by 60, we end up with approximately 0.275 radians per second. And that turns out to be the answer for the angular velocity. 0.275 or 0.28 if it went around to the hundredths. Does it tell me what I want to round to? They didn't this time. I'm going to leave it at 0.275 until we decide what we need. But this idea of dimensional analysis is going to be important, but because it's going to allow you to take information given in the incorrect units and convert it to the information that you need in the correct units. We were given revolutions per minute. Rotations and revolutions are the same thing. And we were asked to provide our answer in radians per second. So I wrote out what we were given, 2.625 revolutions in 1 minute. And then I remember that you can convert a minute to 60 seconds. And I wrote the 1 minute on top here because the 1 minute was on bottom here and I wanted them to cancel. And I wrote the 1 revolution on bottom here because I had the revolution on top here and I wanted those to cancel. That leaves me with my radians in the numerator and my seconds in the denominator, which is what I wanted up here. Then you just have to be careful with the numbers. I had to multiply 2.625 times 2 pi because those were both in the numerator, and I multiplied 60 by 1 because those were in the denominator. Once you get down to here, you do have to divide to get your final answer, which was 0.275 radians per second. Okay, so we need to talk about linear velocity. So remember earlier when I said if you make a certain number of revolutions, let's say we make 2 revolutions, that's 4 pi radians. So 4 pi radians, that's a little over 12 radians, right? Because pi is around 3. What that means, when we say 12 radians, we mean if we took the radius of that circle and lined them up end to end 12 times, that's how far we would have traveled. 12 radians. It's dependent on how big the radius is to figure out how far you went. Well, this idea of linear velocity is taking that into account. We're going to figure out our angular velocity, and we're going to multiply by however long a radius is, however long the radius is. So we use the letter V for linear velocity. And what we do is we multiply the length of the radius times the angular velocity, pi over t, or not pi, theta over t. So you're just incorporating the length of the radius to figure out how fast you're going in linear units. Linear units are like meters per second or miles per hour, rather than thinking in radians per unit of time. Let me show you what I mean. In example 4 here, we're asked to determine the linear velocity of a point rotating at an angular velocity of 17 pi radians per second at a distance of 5 centimeters from the center of a rotating object, round to the nearest tenth. So they're giving us a couple of calculations here, a couple of values. The first value is we're told that the angular velocity is 17 pi radians per second. We're also told that our object is 5 meters from the center. That's telling us how big the radius of the circle is. Okay, we're 5 meters from the center, meaning our radius is 5. So when I do this calculation, my V, my linear velocity, is going to be my radius, which is 5 centimeters, times the radians of 17 pi, oh goodness, and over 1 second. And when you multiply that out, you end up with 85 pi. But we want to round this to the nearest tenth, so we want an actual linear type measurement. So we're going to multiply that and get, 267.0 when you round it off to the nearest tenth. 267.0, and the units of measure is centimeters per second. Now I want to take a minute to show you why these units are centimeters per second. If we do the dimensional analysis in this and write it out specifically, we would have 5 centimeters per radian, right? Because a radius is 5 centimeters, times 17 pi radians over 1 second. And notice the radian cancels, right? This radian and this radian cancels. And then you end up with just what we calculated before, which is 267.0 when you round it off. Centimeters on top here and seconds on the bottom here. And a lot of times we just write that as cm over s. 267.0 centimeters per second. Oh goodness. And again, the way we did that is we did radius, the length of the radius, times the angular velocity. We're counting out essentially how many radiuses we can cover in a second, and that's 267 centimeters. We can cover 267 centimeters in a second, traveling at that angular velocity of 17 pi radians per second with a radius of 5 centimeters. So now we're going to go back to that carousel example, and we're going to figure out what the linear velocity is for each of those riders on the carousel. So just to remind you the situation, we have a carousel with 2 rows of animals. One of the rows of animals, one of the circles of animals is located 11 feet from the center, and the other circle is located 20 feet from the center. We computed in the last example the angular velocity of 0.275 radians per second. I think you'll remember that calculation. We are going to try and compute the linear velocity for each rider. Okay, so the angular velocities are actually the same. It doesn't matter where you're sitting on the circle, you're still covering the same number of revolutions. But the linear velocity is going to be different, so let me show you what I mean. Each of them has a different radius, so we have to do the calculation twice. So this is for the 11-foot row. I'm going to calculate V to be 11 times 0.275. And when I do that, I get approximately 3.025, and that's going to be feet per second. Because there's 11 feet in that radius. And then at 20 feet, my computation is V equals 20 times 0.275. I wrote that very wrong. How about 0.275? There we go. And when I multiply that out, that becomes something like 5.5 feet per second. So when you're on the outside edge of this carousel, you're actually traveling at a faster linear velocity than you are on the inside because you're covering more ground. You're covering more ground at a 20-foot radius than you are at an 11-foot radius. But since those two riders are staying in the relatively the same position, the outside rider has to travel faster. That's actually a very, very basic example of relativity. But in terms of what we're doing, the way we calculate this is we take the length of the radius and we multiply by the angular velocity. Length of the radius times the angular velocity. And that's how you get the linear velocity. Just over 3 feet per second for somebody riding on the inner row of animals, and about 5.5 feet per second for somebody on the outer edge. Okay, we're just going to do one more example and we'll wrap this video up. Okay, so here's a little lesson in how we figure out miles per hour on your speedometer based on the speed that your wheels are turning. So we're told that a race car has tires with a diameter of 30 inches. Now remember, everything we're doing is based on radius, so right away I just know that the radius is 15 inches. Okay. And I'm told that the tires are turning at an angular velocity of 2,000 revolutions per minute. So I've got a radius of 15 and an angular velocity of 2,000 revolutions per minute. We're supposed to determine the speed. That's a linear velocity, but we need to get our answer in miles per hour. Determine the race car's speed in miles per hour. So remember, linear velocity is just the radius, which in our case is 15 inches, times the angular velocity, which they've given us in terms of revolutions per minute. Now, those units don't help us because we need to be in miles per hour. So we have to multiply by a bunch of conversions. I want to end up with hours in the denominator. So to do the conversion for the hours, I happen to know that there are 60 minutes in 1 hour. So these minutes are going to cancel. I'm going to go ahead and cross them out right now. And now I have hours in the denominator, which is what I want. Now, I don't want revolutions in my answer. I need to get to miles. And to do that, the first thing I need to do is get my angular velocity in terms of radians. So I happen to remember from the other problem that to convert to radians, I multiply by 2 pi. So I got to go 2 pi radians over 1 revolution, right? And remember, here's there's 15 inches in 1 radian, 1 radius. So that radian is going to cancel too. So check this out. The revolutions cancel here, and then the radians cancel with the mysterious radius that's written down here, right? 15 inches in my radius. So that guy's gone. Now, I still need to get rid of the inches because I don't want inches per hour. I want miles per hour. So how in the world do I figure out how many inches are in a mile? Well, first of all, I know that there are 12 inches in a foot. So 1 foot is 12 inches. That cancels the inches, and that gets me to feet. Inches are gone. And then I happen to remember that there are 5,280 feet in a mile. So 1 mile is 5,280 feet. And that cancels my feet because I have 1 on top and 1 on bottom. Okay, so if I clean this up, in the numerator I've got 15 times 2,000 times 60 times 2 pi times 1, we don't need to worry about the 1, divided by 1 hour times 12 times 5,280. So I'm going to put 12 times 5,280. And if I do this calculation, I should end up with my miles per hour. And so when you're typing this on your calculator, just be careful. Make sure you include the numerator and the denominator in parentheses. And then when you hit equals, you should get approximately 178, we'll call it 0.5, and this is in miles per hour. Miles in the numerator and hours in the denominator. That's a lot to figure out. Just remember that you have to get from the units you're given to the units that you're expected to calculate in. And to do that, we had to do some conversions. I had to convert minutes to hours, and I had to convert inches all the way to miles. And I did that in 2 steps. I went inches to feet and then feet to miles because those are the values that I remembered. So this car is going about 178.5 miles per hour if a 30-inch diameter tire is spinning at 2,000 revolutions per minute. Okay, lots of examples in this video. Let's just quickly summarize what we learned, and then we'll get to our assignment. So we essentially learned about 3 new things. We learned about angular displacement, angular velocity, and linear velocity. For angular displacement, remember, that's just the revolutions times 2 pi. And that will tell you your angular displacement. That's how many radians you travel. For angular velocity, I'll slide that up a little bit, we learned a new symbol, omega, looks like a fancy W, and we learned that that was the angular velocity, that was your angular displacement divided by the time. So radians divided by time is basically what we're talking about here. Right? This is just radians. When you get an answer for angular displacement, you're getting radians. When you're doing angular velocity, you're getting radians over time, like radians per second or radians per minute. And then linear velocity is converting that angular velocity to a linear unit of measure. And the way we do that is we multiply the length of the radius times the angular velocity, which was computed by theta over t. So in terms of what you're actually multiplying, it's the length of radius times the angular velocity. Jeepers creepers, my handwriting is terrible today. It's probably terrible every day, but it's extra terrible today. Length of the radius times the angular velocity. And those measurements vary, but something like miles per hour or meters per second, some linear measurement over time. Now remember, when you're doing linear velocity in particular, you may have to use some dimensional analysis to get the correct units that the question is asking for. And I can help you with that as you practice these. So give these problems that you're being assigned a try, and we'll see how it goes, and then we'll move on from there. Take care.